Okay, so what are we talking about? What are we covering? So now that we've introduced sequences and series, we need to discuss a type of integral that is needed when convergence of series. And these are improper integrals. So the general idea is, for example, given by the following graph. So suppose we have maybe f of x equals whatever x. And we fix a here. And we maybe choose like b not to be there. And obviously the definite integral from a to b is just that area. But what if we extend b further? Then we have this area here. So you can think of this almost as there's a sum there. Here's a sum here. Maybe b2. There's a sum there. And you're adding this off to infinity. So in particular, what we're looking at is, well, first we need to assume f of x is continuous. But we're really looking at an integral here, where the integral goes from a to infinity. If we continue this process on, that's what we're looking at. So in a sense, improper integrals are summing and adding those sums, right? And this is why I like to cover sequences and series before covering improper integrals, because these are more similar to series than anything else. So how do we define this, right? How do we calculate this infinite right here? Well, because this is calculus, we should know that there's going to be a limit involved. And it's as simple as evaluating this definite integral. So actually, f doesn't have to be continuous on all of R. It just has to be continuous on a to infinity. Okay. So this here is an improper integral. And there's others. So this is just like one. Another one would be, so assume f is continuous on negative infinity to b. Then we can also define this integral in an analogous way. Right? If we were to fix b and vary a this way, we take a sum all the way to negative infinity. And likewise, we just write this as limit as a tends towards negative infinity of this improper integral. Wow, that is a really good integral sign. I don't draw them that nice often. Okay. And then finally, there's one more that we can define. And in a valid way. And that's if we just take A and B and we let them both go to negative infinity and infinity respectively. So under that scenario, if we assume f of x is continuous on all of R, then we can define the integral from negative infinity to infinity as the sum of two of these. So it's going to be the limit as, let me make sure that I'm saying this right. Yeah, I'm not even going to write the limits. I'll just write, because these two are defined, I can just write it like this. The integral from negative infinity to c f of x dx plus the integral from c to infinity f of x dx. So these are the three forms of improper integrals. And they're not difficult to deal with, actually, because we know so many integration techniques by now. We spent like an entire week going over integration techniques. If we can just evaluate this definite integral, then all we need to do is take the respective limits to find out what this sum is really going to be. So let's look at this example. Yeah, this is a good, perfect example. Let's look at, say, the integral from 1 to infinity of 1 over x dx, which corresponds precisely to that picture here. There's 1. We want to know what that area converges to. Well, this is going to be equal to the limit as b tends towards infinity of the integral from 1 to b 1 over x dx. So we can just ignore the limiting process and focus in on this definite integral. We know how to do this. We know what the antiderivative of 1 over x is. So this is going to be equal to the limit as b tends towards infinity of, what is it, natural log of x evaluated from 1 to b. Okay, so then this is equal to the limit as b goes to infinity of natural log of b minus natural log of 1. There's no limit on this side because there's just a 1 right there. But we see that that goes to infinity. The limit as b goes to infinity of natural log of b, it goes to infinity slowly, but it still goes to infinity. So you'll have infinite area, even though it's getting smaller and smaller and smaller. It at a very slow rate, it's still going to infinity. Okay. So let's look at another one. 0 to infinity. Okay, so we want to know the integral 0, say, to infinity of e to the power minus x dx. Wow. You gotta admit, my handwriting is good today. I like these. Okay, so we have e to the power of minus x. We have this improper integral, so we need to first write it as a limit, right? So this will be the limit as b goes to infinity. The integral from 0 to b of e to the minus x dx. All right, so now that we've converted our improper integral to a limit of a definite integral, we just need to evaluate this, right? And this is just negative e to the x, right? Negative e to the negative x. Sorry. Negative. And this is from 0 to b. This is from the limits. B goes to infinity. Negative e to the minus b. Minus and minus and plus e to 0. Minus 0, but it doesn't matter. So that right there, that's like I guess we'll just write it like this. That limit is like that, and we know that's going to go to 0. So this goes to 0, and that just goes to, that's just 1, right? That's kind of surprising. Why is that 1? That's strange. That's really interesting that that's equal to 1. Do y'all not find that weird? That's the exponential decreasing function. And the area under the curve is 1 for that. I don't know, that's interesting to me. Okay. All right, so what's another one? Zero to infinity. If you did all of the homework problems that I had suggested, you should definitely recognize that immediately. You have sum of squares in the denominator. There's no square root. Immediately, I'm like, oh, arcane. It's funny how many of these things I forgot until I was teaching this course, and it was like, oh, I'll never forget that now. Okay, so first thing first, though, we need to rewrite this as a limit of a definite integral. Like so. And then we see that, oh, that definite integral is arctan. So then what is this going to be? Got this limit here. Arctan of 0, that's when sine is equal to 0. So it's just 0, right? And then this, the limit as b goes to infinity. What does that go to? I know, okay, so at least like, we all know that's 0 by now. So this, as p goes to infinity, how does arctan behave? How does it behave? Oh, so it's basically saying what angle gives you infinity? What is that? It's pi over 2. Because at pi over 2, cosine is going, cosine is going to 0, sine's 1. So tangent is going to infinity. Yeah, it's pi over 2. It's because you're dividing by 0, because cosine is equal to 0. Okay, but these are all this form. Let me see if I can find one that's a different form. Oh, I got a chat message. Let me check. Hey, thank you for that. Yes, those are the best integral signs I've ever had. Okay, so actually, I think that's enough on these types of improper integrals. Now, we should mention improper integrals with discontinuities. So there's two main types of improper integrals. There are improper integrals involving infinities, but then there's also improper integrals involving discontinuities. So if we assume f of x is continuous on a b, okay, and has a infinite discontinuity at b, then we have this integral from a to b, which isn't necessarily, it's not defined in a sense that, okay, just imagine this. If we evaluate this improper integral and then we try to plug in b, and there's a discontinuity of that antiderivative of b, there's going to be a problem. You won't be able to evaluate that improper integral. So, because b, so b's on the right-hand side of the continuous domain of f, we're going to evaluate this as a limit from the left of this improper integral. There's another good integral sign, by the way. All right, so even though we can't evaluate the antiderivative at b, right, there's an infinite discontinuity there, we can still, because the function is continuous from a to b, we can still take the limit of that function as it approaches b from the left. And that's what this is saying. It's kind of a natural way to fix it, right? Like you can't plug it in, but you can still look at how the function behaves as x tends towards it from inside an integral where you are continuous and you're smoothly approaching b. And then the same thing can be said for the other way, right? So f of x is continuous on open interval a to b. You can probably guess what we're going to do. And has an infinite discontinuity. At a, then the integral from a to b of f of x dx. Now we need to approach a from the right instead of the left, right? Because we're going to be heading that way. We can't evaluate the antiderivative at a, but we can still look at what happens as we tend towards a. Okay. Let's see. There. Okay. Same concept. And in an analogous way, if we are not continuous at either a or b, then we can have a sum and look at the left and right hand limits as they tend towards a and b. And this will fix all the problems that you could run into when you try to evaluate these at infinite discontinuities. So maybe we're going to look at an example or something. Let's see. Yeah, this is a good one. So let's look at the integral from 0 to 1 over the cube root of x dx. Okay, so notice here that the function has an infinite discontinuity at x equals to 0. It blows up, right? It blows up. I don't know why they use infinite discontinuities in place of vertical asymptote. I'll have to think about that, but it's definitely vertical asymptote at 0. It blows up, infinite discontinuity. So this is one of these improper integrals. So we know we need to do something about that 0, which we can do with this guy. So we're going to say the limit as c approaches 0. Now we need to go from the right-hand side, right, of the definite integral from c to 1. And I'm going to go ahead and rewrite that as x to the power 1/3 or minus 1/3 dx. Okay. So now we just evaluate this. So what is that? 1/3 plus 1 is 2/3. Divided by that is 3/2. So this would be the limit as c approaches 0 from the right. 3/2 x to the power 2/3 evaluated from c to 1. Okay, so now this becomes the limit. C tends towards 0 from the right. 3/2 x to 2/3 minus, anyway, it's just 1 times that, right? Plug in a 1, it's just x to that, so it's 3/2 minus the limit c tends towards 0 from the right of 3/2 c to 2/3. Did I do that right? Yeah. And that's it, because this just goes to 0. That's just 0. It's just 3/2. Okay. So I think that's pretty much all I needed to cover from section 8.8. In order to use this knowledge to test for convergence of series, which again, my video on series did not post to YouTube yesterday properly. I think there's an error. I'm trying again right now. It says it has 15 more minutes, but I talk about series in that video. And we are concerned with convergence of series, and improper integrals will give us a test for convergence. So that's why we needed to cover it. So I think that'll be it for this lecture. From this section, suggested homework. Yeah, I think 13 through 45 on fair game for something on the final exam. Okay, so that'll be it for this recording.